So when we get to if you go to YouTube, you can see the Some Prof channel is streaming at this point, and I'm just confirming and double checking. Yep, it is. And I'm gonna screen share on the Discord side. So if possible, use Discord to watch the live stream because Discord is more responsive. YouTube has a lag time of about 10 seconds, which is really not suitable for what we are doing. And there we go. All right, so I'm gonna let you guys, spend, maybe 10, 20 seconds or so you can configure. You can basically peel off the live screen, the live stream screen, and peel it off, off of the desktop app. So this way you can, watch the video on one side and be able to watch the text on the other side, and potentially even have your browser up at the same time. Kind of depends on your screen resolution and the size of your screen. All right, so we are gonna get started right away into the class content because I made a video to talk about the syllabus. So please watch that video if you have not done so. At this point, all the announcements will be done through the Canvas interface. So if you missed something, you can always go back to announcement in Canvas and basically read all the announcement postings again if you need to. All right, so I'm looking at the text channel, and occasionally when I see people typing, I might pause a little bit just to make sure that there are no questions. And this is also the first class, so I want to make sure that everybody can make it in the class. And I'll do one more check, just like I promised. And yeah, go ahead. The daily. Yeah, so the daily is going to capture everything for that particular day. So typically, it's going to be topic specific. The general text channel is just, general. I mean, topics that are not specific to a particular day, would go to the general channel. So I will watch both of those. The only one that I do not watch would be the off-topic one, just in case somebody gets bored in the class and want to, start some off-topic, discussions on the side. So that's perfectly okay. Not possible in a real class, but in a class like this, hey, it's not a problem. All right. Yes, I do, Eric. I do read the text channel as I teach. So I turn off the notification because otherwise, you guys, well, you probably won't hear if you're just not subscribing, but if you're just watching through the Discord screen share. But all the sounds, all the system notification sound will, you can hear all of that from the YouTube recording. All right, so we'll go ahead and get started because the syllabus is basically done already. If you have not, once again, if you have not watched my video that talks about the syllabus, go ahead and watch that. If you have any questions about the syllabus, you can either direct message me or you can post those questions in the general text channel. So what we'll do is, I'm still kind of debating what I want to do first. I will start. Yeah, go ahead. I am recording right now. I'm streaming. You mean the video? Yes, YouTube is my DVR. You can, in fact, look back about 10 years. Yes. So you can not only can you watch or rewatch recordings of this particular summer session, you can actually go all the way back to about 10 years ago when I first started to record all my lectures. Yep. So I am going to post. I'm going to bring up a few interesting topics first. The first one is MBTI personality assessment. I am not going to click it, okay? Okay, so Eric, you might want to mute because Eric, thank you. All right. So the MBTI personality assessment is interesting. If you have never done a personality assessment before, um, I think it doesn't hurt, okay, to do a personality assessment, just to find out, what your strengths are, and I think that is important, okay. And the earlier you do this, the better. Um, all right, so that is a little detour, and now we're gonna get back to the first module. I do talk about these modules, sequentially. So on Tuesday, tomorrow, if you can read ahead of me, that would be terrific, because being able to read ahead of me, read ahead of the lecture, basically means that you would have some understanding of the terms. Even if you don't have 100%, you will still have some understanding of the terms before the lecture starts. And hopefully you also have time to write down some questions. If my notes is cryptic, which some people have told me, then you can write down some of those questions, and when we get to that topic, you can then bring up the question so I can answer those questions in the right context. So having said that, the first one that we are going to click on is physical states, truth, numbers, and computers. So the way I teach this class is a little bit different compared to how other professors teach assembly language programming, in quotes, okay? The reason why that is the case is when I taught this class the same way as everybody else, I would have exams and I would find out that most people, a lot of people, do not really understand what is going on inside the processor. They think assembly language is syntax based, so putting parentheses around something means indirect and so on. The answer is no, that is actually not the case, okay? Because what a processor can and cannot do is dictated by the processor architecture itself. It is not the syntax. The syntax is nothing more than a dressed up language so that we can specify the instructions more easily. But the actual mechanism is dictated by the processor architecture. So that's when I started to kind of change the way I teach this class to start with computer architecture. So the actual programming in assembly language won't start until about midway through the entire session. So for us, it's going to be about week 4 or week 5 or so, depending on the pace that we can do in this class. All right, so I'm not seeing any text traffic, so we'll go ahead and move into this module. Okay, so all of the modules that I have written, they have a sequential number. So the sequential number is simply sequential to when it was written the first time. And you will see a date that is relatively recent. That's because sometimes I refresh the page and that reflects the last time I make any changes to the page. All right, so I'm gonna get into the text here. I'm gonna bump up the font size just so that it's easier for me to highlight the portions. So section 2 basically just talks about the different types of devices and what physical property we use for computers. Section 2.1.1 talks about electromechanical computers. So if you want to know what is an electromechanical computer, the best way to do it is to watch the Imitation Game, the movie. Because in that movie, the character, the character Alan Turing, which is modeled after the actual computer scientist, he was basically building a electromechanical computer. So when we talk about electromechanical computer, it simply means some parts of the computer is actually mechanical. In this case, the armature is mechanical, but the electro part basically means we are using electricity to pass information to control the mechanical aspect of it. So these two kind of interact. Now, modern day, in the modern day, if you want to build a electromechanical computer, you can build one using relays. Okay, you can just go to a auto parts store and look up those relays, 12-volt relays, and you can actually build gates and stuff like that using relays. So electromechanical computers are basically the first generation because they are easier to build, and the mechanical parts, the electromechanical parts were available at the time already. So we're not going to talk too much about electromechanical computers, but it is noteworthy to notice that the entire computer science field, okay, basically took off because of electromechanical computers. At the end of World War II, German Enigma encryption machines would receive a fourth wheel to scramble broadcast communication. This was also reflected in the movie, The Imitation Game, of why something that people were able to do by hand was no longer feasible, because they put in one extra wheel, and that increased the number of possible ways to encrypt messages to the point where it is no longer practical to do it by hand. And that's the reason why Alan Turing, along with his associates, made the first computer to basically decipher encrypted messages. That was the beginning of computer science. So any questions, comments? Nope. Okay, all right. So we are now gonna move on to vacuum tubes. So vacuum tubes is the next generation of devices that people use to make computers. I'm not gonna get into all of these details over here. If you want to, for those of you who are curious, you can right click on these hyperlinks and bring up a new page. So most of these are Wikipedia pages that this one describes how vacuum tube work as a device, and this one here is very specific to the type of vacuum tubes used in the earlier implementation of quote-unquote solid-state computers. So if you right click on this one, it will bring you to the description of a triode. So a triode is basically a switch, or you can look at it as a valve, where it has one end coming in, one end going out, and one more terminal as the control. Okay, so look at this as a valve. Okay, so you have water coming in, you have water going out, and then you also have the part where you can turn it, right? So that's basically what a triode is, with the only exception that the quantity, the physical quantity that it's switching, is also the kind of quantity that will control it. So instead of having a hand to manually turn on and turn off a valve, it's going to be the same quantity, the same kind of quantity that is flowing through the valve that's controlling whether the valve should open or not. So in this case, it is electrical. So that's kind of what a triode is. So I went through a lot of explanation of to explain how a triode work. But for the most part, you don't have to understand that part, because all of this is kind of more of a historical aspect of the evolution of computers. It is it's noteworthy to mention the Lorenz cipher. This one is also in the same era as the electromechanical computer that we mentioned earlier, but this one was is a much more complex cipher, and as a result, the computer designed to decrypt it also needs to be faster. And it's called the Colossus. So the Colossus was a vacuum tube based computer, and its job is to decrypt messages encoded by the Lorenz cipher. So you can really kind of see how World War II, especially toward the end, basically a lot of computer related inventions, were, they happened at the end of World War II, because one side learned how to do the encryption, and then the other side says, hey, I need to be able to decrypt the messages, to know what is actually in the communication. So that's kind of interesting. So now we get to section 2.1.3, where we moved away from vacuum tubes and moved into transistors. And we are still using transistors now. And there's a long description here about the various types of transistors. There's the BJT is bijunction transistor, and there's also the FET, or field effect transistors. So we'll get back to transistors in just a little bit. Section 2.2 talks about physical states. Okay, so what are we dealing with physical states? So physical state, can be, different types of physical quantities. In a modern computer, we use electricity. So we use the flow of electricity. We know that as current in a physics class. We can also use what is commonly known as voltage. But voltage, the technical term of voltage is electrical potential, okay? Or vaguely it is related to pressure, okay? So those are the physical quantities or physical states that we can use to represent stuff, okay? So we can say, well, a high voltage means 1 and a low voltage means 0. So we can assign interpretations to those physical states. Now, the most important part is we also need the valves, okay? We also need valves that are controlled by the very same physical states that it switches on and off. So in this case, when we talk about transistors, so the transistors that we are going to explore has one terminal called the gate, and it has one terminal called the source, and one terminal that is called the drain. So flow would normally go from source to drain, but it is controlled by the gate. So the gate is where you can, quote unquote, use your hand to turn it on and turn it off, and the flow is just going through the valve. So the important part here is they have to be the same kind of physical quantity. So if you're using water, okay, you can build a water-based computer, by the way. But if you use water to build a computer, then the material, the quantity that is being controlled, which is the flow of water or the pressure of water, it needs to be controlled by, guess what? Water again, okay? Either the pressure or the flow of water. So we'll definitely get to see more of this discussion in just a little bit. Section 3, I'm just looking at the text channel. Nope, no questions yet. So I know I'm moving through this material really fast because, when we get to section 3.1, then we need to slow down because that is when we actually get to do something to play with. Today's lab allows you to play with transistors, but without actually doing anything physical. So section 3 talks about truth, okay? And we are talking about truth as in Boolean algebra type of truth. So the question is, so inside the computer, we have heard about this, that everything is either true or false, right? So what exactly is true and what exactly is false? That really is just an interpretation, okay? We are basically just saying any voltage above a certain threshold is interpreted as true or 1, and any voltage below a certain threshold is interpreted as a 0 or false. Okay, so it's just a label. So now we're going to explore transistors. So we'll get back to the truth, false, 0, 1, why that is important. But before we do that, we'll talk about two very specific types of transistors. Here's a question. So analog versus digital has to do with how we do the interpretation. With analog circuits, then all the voltages in between there's no such thing as a threshold with an analog circuit. So with an analog circuit, the relationship between the components is it's purely mathematical, and we are talking about continuous math. So we are talking about differential equations, calculus, and so on. So those relate to analog circuits. The digital circuits, on the other hand, is based on a digital interpretation of the voltages. So it's not like the voltage itself, okay, is digital, because that is not possible. Okay, the voltage that you measure at any point is a continuous function. In other words, you cannot change the voltage of a point in the circuit from 0 to, let's just say, 1.5 volts without going in between all the voltages in between, and there's an infinite amount of voltages in between. So that's a continuous math kind of thing. But when we interpret the voltages in such a way where above a certain threshold is true and then below a certain threshold is zero or false, that is a digital interpretation of the voltage. So it's a matter of interpretation. The transistors used in a digital circuit can also be used, in an analog circuit, not in the same configuration, but there's no difference. Okay, it's not like there's one kind of transistor called a digital transistor and another type of transistor called the analog transistor. There's only one type of transistor. It is how we build the circuit and how we interpret the voltages that makes a particular circuit digital and make another circuit analog. So hopefully that answers Joshua's question. Does that answer the question? Okay, great. All right, so we are going to look into a N-type transistor like this one. And this is actually technically a MOSFET, which is the abbreviation of metal oxide semiconductor field effect transistor. Well, it's a long name, but we are not in a physics class. We are not in an electrical engineering class. So we can take a higher, kind of more abstract view of this transistor. And we are going to start playing with Logisim right now. And by the way, today's lab is going to be using Logisim, so you will learn how to download the jar file, the Java archive file, how to start it up, and so on and so forth in today's lab. On the other hand, I am going to use my own terminal here so that you can just kind of get an idea of how to start it. This is also a good time to kind of segue to talk about what environment should you be using to do your homework. Okay, there are three major operating systems that I'm aware of. Okay, one is Windows. Most of you are probably using Windows. The second one would be Mac OS, and I guess those of you who are not using Windows are using Mac OS. And there's also Linux. I really doubt maybe two people in this class would be using Linux, myself being one of them. But I'm just going to use Linux here. Oh, okay, great. That will be you. That's interesting. That's funny. So I'm going to use command line tools a lot. Okay, so you have to think about how to do it on your side. So on the command line, you can start up a jar file, by typing Java, assuming you have Java already installed. Java-jar, and then here is the file that I have downloaded already. So obviously this command is not going to work for you because you have not have this file downloaded yet. But today's lab is going to have the instruction of how to do it. Okay. Now this command is not unlikely to work for those of you who are using Windows, because first of all, the slash is in the wrong direction. Okay, because in Windows or DOS you have to use backslash instead of a forward slash. And then this little tilde symbol, which is shift backtick on the keyboard, means the home folder in Linux and also Unix. So Mac OS X is close enough that this command may work depending on where the jar file is located. But in Windows, it's going to be quite different. Okay, so those of you who are using Windows, now you have a choice. Okay, I'm pretty sure I presented that as an option already in one of the announcements. You might want to consider, maybe not, but you might want to consider getting Windows Subsystem for Linux, WSL2, because that allows you to run Linux alongside with Windows, but without using a whole lot of resources, because it's a lightweight hypervisor that's actually doing the job of creating a virtual machine. So it's not really heavy duty. It doesn't use up a lot of processing power, and it's free. And it's published by Microsoft. So that would be my suggestion, okay, for those of you who are using Windows but you want to be able to use the same commands that I use in class. So I'm gonna start this up, and here is Logisim. There we go. So Logisim looks like a drawing app, but it's actually quite a bit more than that. So what I'll do, this is actually the first time I, do something like this, is I'm going to go into wiring. So this is the user interface of Logisim. Logisim actually has not been updated for a long time, so it really is kind of archaic compared to more modern applications. So now I'm going to pull up some components. So this window here allows you to select components. And if you, let me see which one I want to click on. Okay, I want to get power. Okay, so if you want to place a power component onto your circuit, so you just have to click on power over here. And I'm not talking about right click. I'm talking about just a usual left click. Okay, and don't drag it. There's no need to drag it. Just click it. And because the click is selecting the component, and then then you can just go ahead and place it anywhere you want in the actual circuit area. So let's just say I want to put it here. Then you just click again, and the component is going to be here. If this is too small, you can always control the zoom. Zoom control is over here, and I'm just gonna let me double check to make sure you guys can see that portion. Yep. Okay, so zoom control is over here, so you can make it a little bit bigger, make it a little bit smaller, and as long as the tool you have selected is the arrow, you can drag the component around so you can reposition the component any way you want. You can also see the properties of the selection. So in this case, this is what we call quote-unquote power supply. So it doesn't really have a whole lot of attributes. One is which way it faces, so it can change the direction. All it does is to change which way change the direction of the component. And data bits really should not really apply in this case, because this is just power. And you can look at this as the plus terminal of a battery. Okay, so this is the plus terminal of a battery. And compared to that, this would be the other side. This is going to be the negative end of your battery. This is positive voltage. This is the source of all positive voltages. This is the source of all the negative voltages. So current will normally go from here to here. Okay, but we don't want to make that connection here, because that would not be a good idea. So what we'll do is we are going to place a component into this circuit. In fact, I'm going to place all of the components into this circuit, and then we'll talk about what those components are going to do. So we are going to put some transistors. So once again, you have to locate the component that you want. In this case, it is a transistor. Click, just one single click. You can see, it would give you the type or the attributes of the transistor, but don't change anything yet, okay? So we'll just go ahead and place the component here, and then we'll see what we can do with it. Oops, sorry. I meant to move this component, so click it first and then drag it. But don't drag the terminal. That was my mistake. And now I have undone too much. Oh, it doesn't have a redo. Never mind. Okay, click on it. Make it go face north again, and get the ground, put it all the way down here, and then we'll pick one transistor. and put it on the screen like that. All right. So right now, what I want to do is to really take a closer look at a P-type transistor and identify, how can we tell which end is which end? Okay. So what we'll do is we're gonna zoom in a little bit and click somewhere else so that the component is not selected. First of all, we notice there's a little bubble over here, right about here. That bubble tells us that this is a P-type transistor. All right, so let's go ahead and change it to an N-type transistor. Click on it first, and then you can see in the selection the property of the selected component, it says this is a type P transistor. You can change that. Okay, just about everything inside the attribute list can be changed by using a drop-down list. So in this case, I can change the type to an N-type. So don't blink. This is our N-type. Okay, so what is the difference between a P-type and an N-type transistor? The circle, exactly, the little bubble, right? Okay, so with the bubble, it is a P-type transistor. Without the bubble, it is an N-type transistor. Very good. Good observations. So now what we'll do is we'll identify the three ends of a transistor. This end, is called the gate. Okay, the gate is the control terminal of the device. Okay, in other words, if you specify a 1 or a 0 at this terminal, it will either open the valve to allow the flow, or it will turn off the valve and therefore disconnecting between the other two terminals. So that will leave us with the other two terminals. One is source and one is drain. I will let you guys guess which one is the source and which one is the drain. Does anyone want to give it a try? That's right. It is going to the right. Now what gave it away? Exactly. Okay, so the arrow is always flowing from the source to the drain. Okay, so we have gate, source, and drain. Now, what about how do we turn on the valve, right? So the question is, this is a valve, which means, the source and the drain can be connected. It can also be disconnected. So the question is, how do we control that? The gate is responsible for that. So now here is the explanation of why there's a bubble here. So with a P-type transistor, if the gate has a high voltage, then the flow is not allowed. Okay, let me say that one more time. With a P-type transistor, if the gate has a high voltage, then the valve is off, which means it disconnects the source from the drain. All right? So what do you think we should do to turn on a P-type transistor? Use the other voltage, right? Okay, very good. Reverse is good, but it's using the other voltage. So to turn off the device, we use a high voltage, which means a low voltage as the gate is going to turn on the device. Okay, so that is counterintuitive, but that's also why there's a bubble here, because the bubble means negation. Okay, in the circuits we'll see later in this class, the bubble means negation. So in this case, the bubble basically says, when there's a 1 here, when the gate is true 1 high voltage, then the valve is off. When the gate is low, 0 or false, then the device is on. And that's why there's a little bubble here. So now that we understand what a P-type transistor is, okay, the 3 terminals, let's take a look at an N-type transistor. So an N-type transistor, once again, looks almost exactly the same as a P-type transistor, but without the bubble. So can anyone guess how we turn on an N-type transistor? How do we specify and say we would like to have current to flow from the source to the drain? What should be specified at the gate? Exactly, high voltage. Very good. So between the P-type and the N-type, it would appear to us the only change is one uses a high voltage to turn on, the other one uses a high voltage to turn off. So that seems to be the only difference. Well, that's not exactly true. Okay, there's one more thing that is different. And that one is going to be a little bit tricky because what they're controlling, the so-called flow, is also different. With an N-type transistor, it is controlling the flow of electrons. Okay, so electrons will flow from the source to the drain, which also means the source should be closer to the ground symbol. With a P-type transistor, let me change the type first so that we can talk about that. So with a P-type transistor, the source would be the voltage, would be the supply voltage, would be the high voltage. So the direction of the flow is opposite between the P-type transistor and the N-type transistor. Just remember this, okay? P is positive, so the source of a P-type transistor should be at a higher voltage. And N means negative, so that means an N-type transistor should have the source closer to the ground or the negative voltage. So now we're going to build a circuit. Okay, so we'll zoom out first, and we're going to build a circuit. So for those of you who have your browser open, onto the same document, the circuit I'm going to build is down here. Okay, this is the circuit that I want to build, and this is also what you're going to have to build for tonight's lab. So the steps that I'm taking right now, will be about the same steps that you would need to take. So let me switch back to Logisim right now. So we need, yeah, go ahead. Yes. That is explained in the rest of this module. Also in your lab. So your lab and also the rest of the module will talk about that. But that's a very good question. Okay, what are we building? It's actually, I'll put it this way. That was such a great question because we are going to build everything. Okay, I shouldn't say that. Everything that we are going to talk about in this class can be built using a simple circuit like this. Just a whole lot of these, okay? But if you think about one of these things as one quote-unquote gate, by having enough of these gates, we can build the computer, the processor architecture that we'll be programming in about week 4 or week 5. Okay, so that's a very good question because we are basically building the smallest component right now that can be used to build an entire computer. Now, is it actually being done that way? The answer is no, but it can be done that way. Okay, so very good question. But right now, I'm going to demonstrate how to use the tool. So you know that we need to change the orientation because the P-type transistor is supposed to be kind of vertical to make it look nice. So we are going to click on this one, and then we change the heading or the facing. So right now the facing is east, and we want it to face south. Okay, so change it like that. Because remember, this is a P-type transistor because of the bubble, and it is controlling the flow from high voltage to low voltage, and therefore the arrow needs to go down in this case. But we need one or more of these, so to make one more is easy. Control D on the keyboard, or you can go to once you have a selection, it doesn't even have to be a single component. You can have multiple selections or a selection of multiple items. Then you go to Edit, and then you can select duplicate or just type Control D, and it will make a copy of whatever you have selected, and you just have to drag it to wherever you want to place it. Okay, let's just say over here. Oops. Okay, let's just say over here, and now we have 2 P-type transistors. Now switch back to the diagram. We have 2 N-type transistors down here. So now, instead of having to, drag and drop and then rotate, I'm going to do the lazy part. Okay, we'll select both of these, Control D to duplicate both of these, and kind of, okay, that won't work. I'm going to have to do it again. Control D, and you have to drag it, using the part that is gray. Okay, that doesn't do it either. One more time. Let's give it another try. Nope, it won't do it. Okay, now I'm obsessed. Alright, maybe not. Gonna have to do it one by one. There we go. Alright, so we select one, and this is not the right type anymore. So what we'll do is we'll change the type first. So changing the type once again is having the components selected, and you can only use this arrow tool to do a selection, and then we change the type from a P type to an Ntype. So now the bubble goes away. But when the bubble goes away, it becomes an N-type transistor, but the flow direction is wrong now, because an N-type transistor is controlling a flow that is going from the negative end to the positive end. So now we need to change this around to make it go quote-unquote up. So now we change the phasing from south back to north, like that. And we're going to need another one of these, so Control D again. And now we have all the components that we need, just about, not everything yet. Because in the circuit, we also have these two, they're input pins, and this one, which is an output pin. So back in Logisim, the input pin is right here. Now I know there's also a pin down here, but that one is not as good to use, okay? So when you need to specify an input pin, use the one on the toolbar and not the one inside this pane over here. So we're going to put two of these, okay, on the circuit, and we need one output pin. So going back to the original circuit, this is our output pin, and it's just a little bubble going like that. So now is also a good time to talk about what an input pin really is. An input pin is kind of like a pass by value parameter. So it basically gives a circuit something to process. The output is kind of like a pass by reference parameter, but it's more like a return value of a function in C or C++. So that's how you can see, the input pins, they are parameters, and the output pin, which is a return value. So it's time for us to actually make the connection. So if you are, an artist outside of this class, you can, kind of try to make everything line up and look nice, okay? All right, so now is a good time to talk about the different types of junctions. If I want this terminal to connect to exactly the same logical connection as this wire over here, and by the way, this is called a wire, and you can create a new wire just by dragging and dropping like that. But you can see there's a little bubble here. This bubble means this wire is actually electrically connected to this wire over here. So now we're going to draw something that does not connect. Okay. Okay. We'll keep connecting things, and then at some point we'll draw something that does not connect. All right. So let's just say we want to connect this one to this input pin over here. So to line up things a little bit better, I can move this one. Maybe I'll put it down here. Okay. Now obviously there is a way to make a connection to this terminal without having to overlap or cross over the wires, but I'm not going to do it that way because I want to illustrate what happens when you cross over without connecting. Okay, so we'll go ahead and I'm going to cross. I'll choose to cross over here. So I'm going to cross over and then make a connection over here. So when you look at this junction over here, you don't see a dot, right? See, this particular dot is missing over here. which means these wires are not electrically connected. This wire segment and this wire segment are not electrically connected. One is simply flying over or under the other one. All right. So now we also want this to connect to this transistor. Okay, so logically speaking, this is one way to draw the diagram. If you want to make it look nice, you can always make it look nicer. But at this point, we are not too concerned about making the picture look nice. So I'm just gonna finish up all the connections like so, and then the output pin connects to this wire over here. There we go. So now we have built the circuit, and you're gonna have to build it in today's lab, okay? And no, I am not going to save this file and upload it to Discord, because that's kind of the whole point of today's lab, is for you to learn how to use Logisim, right? So now what we want to do is to find out, what does this do? Okay, so that was a very good question. What does it do exactly? Okay, but I can't really talk about that when Logisim is actually simulating. So I'm going to choose to disable simulation. Okay, so if you go to the simulate menu, you can select or deselect, in this case, simulation, and let's see, reset simulation. So everything is now blue, which means the circuitry is not being simulated, and we kind of have to reason out what this circuit is going to do. The timer on my watch just went off, which is a reminder that I'm going to take roll now. Okay, so let's hop onto Canvas, and I am going to specify the word I am going to use for taking roll tonight. Over here, you cannot see it yet. Okay, give me a second here to change the question. Alright, so we're gonna add a new question, and this is gonna be, what is tax word for row taking? And we want to change the question type from multiple choice. Sometimes I forget to do that, which basically means the whole thing is trivial. So I have to change it to fill in the blank, and the word is NAND, N-A-N-D. Okay, so make sure you remember that word, and in fact I'm gonna type it inside the text channel, so this way nobody can say, but Tack, you didn't quite spell out the word correctly. There we go. Update question, and go back to details so I can control when it is due. So how much time do you guys think that it will take you to click on the link, type the word, and then press the enter key? You're still driving. Okay, we'll make it 3 minutes, and for Joshua, I will count you in anyway. So don't worry. Don't try to click on something while you're driving. Okay, just you're fine. Okay, you have my words. Alright, so let's go here and make it do. Okay, today is June 7th, and right now is 6:18. So we'll make it 6:25. That should be plenty of time. There we go. Save and publish. There we go. I can understand that, getting food, but don't try to text and drive at the same time. Alright, so you should be able to see the activity right now. So everybody other than Joshua, go ahead and go to the row taking activity of today's date, which is right below testing a circuit and how Tack grades some Logisim labs. So right here, click on it, and then use NAND as the word. So I'll give you guys a few minutes to do this. question? Oh, right, right. So you are Sima? Sina. Okay, right. Sorry. Yeah, you'll be fine. So there, you're one of the exceptions because I could not add you to the class. Yeah. Yep. Yeah, yeah. Go ahead. Oh, okay. All the possibilities that I did not anticipate. I will change it so that you can do it again. How about that? All right, so let me go here. Nope, allow multiple attempts would do. There we go. Okay, so if you refresh your browser, you should be able to get back to it. I think the exclamation point is a force of habit through because of texting. Unfortunately, Canvas is quite exact, when it's trying to match those things. Yeah, yeah, and I cannot make it use a regular expression either. So can you do it now? Okay, great. All right, excellent. All right, so Paul, are you back or are you still not being able to hear me? I guess that would be stupid for me to ask that questions by using voice. All right, so Paul, yeah, go ahead. That doesn't seem like a very good idea because you'll be missing one or the other class, right? You won't be able to do the lab, would you? Because the lab is right after the lecture. Okay, well, I will let you try to sort out those things, these yeah, sort out between these two classes. All right. Yeah. I'm gonna take, and that's exactly why I'm taking roll. Yep, because people who do not show up today, even if they were on roster, they won't be anymore. Yep, sure. All right. What do we need to do to take roll? Go to the roll taking activity and type in the answer. I guess Barack cannot hear me either because audio is lost. I guess I'll figure out how to deal with this later. Yep. Thank you, Jonathan. That will work. And of course, what I just typed is not going to be it's not going to be very clear. And NAND is the answer. All right. All right. So we only got about 10 more seconds before the activity is over. And I'm going to head back to the module and also the circuit. There we go. Alright, so we're continuing with the analysis of this circuit here. So the first question is, well, let's assume the input pins are exactly the way they are right now, which is 0 and 0. So by the way, 0 is really just the same voltage as ground, and 1 is the same voltage as power. Okay. So right now we have a low voltage of this for this node. Okay, let me explain what I mean by a node. Now you can see that I changed my tool to the poking tool, the hand with the finger out. That's called a poking tool. So when you use the poking tool to poke on a wire, the entire node is going to light up. So we can see there's one wire segment like this, and there's another wire segment like this. But they belong to the same node. In other words, they are electrically connected. If you poke on this one, this is the entire node. If you poke on this one, this is the entire node. Okay, so that's the concept of a node, which is everything that is electrically connected by wires. Okay, so now we want to analyze the circuit. Okay, so let me go back to the selection tool so that I can poke on things without having to highlight the entire wire, the entire node. So we want to analyze the on-off state of each transistor. So let's focus on one at a time. Look at this one here over here. So do you think this particular transistor is on, or do you think it is off? So I guess this does rely on a little bit of memory because we talked about this just moments ago. This is a P-type transistor. The bubble really should remind you how this type of transistor works, okay? Because the bubble says not, right? It is the negation. It is on, okay? Okay, so I'm seeing some traffic on the text channel, so I'm gonna answer the question that Barak asked earlier. Okay, the answer is yes. Okay, there we go. All right, so the answer is for this question, okay, whether the transistor is on or off, whether it's connecting or not, whether the valve is on, the answer is it is on because the gate voltage is low, and because this is a P-type transistor, the gate having a low voltage means the device is on, or it is connecting from the source to the drain. So you can probably say, oh, but then this transistor is in the same boat, right? Because this transistor, okay, let me click on it, is also a P-type transistor. You can see the bubble here, but it doesn't connect to this particular input pin. It connects to the other input pin, which is also 0. So that means both of the P-type transistors are on. They are connecting, which also means the output pin, this output pin over here, it has two paths to connect to the high voltage source. The first path is go through the P-type transistor that is highlighted right now, and then the other one is to go through the other P-type transistor that I'm highlighting or selecting right now. So there are two paths to connect to the high voltage. So let's check out the other two transistors. Okay, so let's check out this one first. There we go. So is this one on or off? So the first question you need to ask is it a P-type or N-type transistor? After you know whether it's a P or N-type, then you look at the gate voltage to find out whether it is on or not. Exactly. Okay, so Jonathan and Fulin are both correct. Okay, this transistor is off. So is this one. Okay, so that means we do not have any path from the output pin to ground, but we have two paths from the output pin to power, which is a positive voltage. So that means the output is a 1 in this case. Okay, if both inputs are zeros, the output is a 1. Okay, so let's go through another scenario. Okay, what if I change one of them to a 1 and the other one remain to be 0? What is going to happen now? So we go through the same analysis. Okay, we look at the first one. Okay, we look at this one first. This one is now off, right? Because it's a p-type transistor and the input or the gate voltage is high, which means the p-type transistor is off, which means it is no longer connecting from the supply voltage to the output pin. But the other one is on, right? If you look at this one is still on because the gate voltage of this P transistor is still connected to a low voltage source, which means it is on. This transistor is on, which also means the output pin has one path in this case to connect to the power. Now we want to analyze the other two transistors, the two N-type transistors, okay, one at a time. So we look at this one first and go like, this one is on because it's an N-type transistor and the gate is a 1 or high voltage. So this one is indeed on. And then we look at this other one and this one is off because this one is also an N-type transistor. The gate is connected to a low voltage, so it is off. So now we have an interesting situation because with the P-type transistors, one is on and one is off. With the N-type transistors, we also have one is on and the other one is off. So what is going to happen here? Well, the two circuits are different. Okay, let me highlight the sub-circuit I'm talking about. So if you look at this particular sub-circuit, it is a parallel circuit to connect to the power because there are two parallel paths, which means if only one is on, then it is on. Okay, we only need one of them to be on for the entire thing to be on. So we do know that the output pin is connected to the power pin over here. When we look at the other part of the circuit, okay, this part of the circuit, these two transistors are connected in series, which means if at least one of them is not on, then the circuit is broken. And we know one of them is not on. We know this one is off. So the circuit is broken. There's no way for the output pin to connect to the ground over here. So that means this, for the entire circuit over here, we have one path to connect to power. We have no path to connect to ground. So the output pin would still be a 1 in this case. All right. And let's look at another scenario. What if this one is a 1 and this one is a 0? Well, kind of the same situation, because if you think about it, the scenario that we just talked about is symmetric to this one over here. All we are doing is switching which one of the two P-type transistor is on and which one is off, and which one of the N-type transistor is on and which one is off. So that's the only thing we are switching. Okay, we still end up with a situation of one P-type transistor is on, one P-type transistor is off, one N-type transistor is on, and one N-type transistor is off. Okay, so same situation. The output is still a 1. So we got a question. What does it mean? What really changes if it can't connect to ground, if anything? If it cannot connect to ground, then the output pin would not experience a low voltage. There's no connection to a low voltage. That's all it means. All right. And then Barak has another question, or is typing. All right, so the question is, what's going to happen if lab can't be done with time frame? And it would still be counted as an absence because it would be an absence of attending the lab session. This is a synchronous class, which means it applies to both the lecture and the lab portion. All right, but we are not quite. Yeah, go ahead. Sorry. Said. Either way is fine. Yeah, go ahead and you can use voice. Mm-hmm. hmm The lab has the same duration as the lecture, which is 80 minutes. No, is it? Yeah, it is 80 minutes, 1 hour and 20 minutes. So you might be able to get it done, but tonight's lab does not even need that. Tonight's lab, you can actually use Windows. Just double click on the jar file. It will start up Logisim just fine. Yeah, there's one portion you need to use the command line, which is really just typing Java on a command line interface, which is known as a CMD prompt in Windows. So that part does not need any type of installation because CMD comes with Windows. Is that okay? All right. All right. So we got. Okay. All right. So we got one last scenario to talk about here, which is what happens when both input pins are ones. Okay. So now we go through the same process. We analyze each and every transistor. We look at this one here. And this is a p-type transistor. The input is, or the gate voltage is high, which means the device is off. Same situation over here. So this time the output pin does not have a path connecting to the high voltage or the supply voltage, which is also the high voltage. What about the N-type transistor? We look at this N-type transistor. The input or the gate voltage of this N-type transistor is a 1, which is a high voltage, which means this transistor is on, it is connecting. We look at this one here, even though it is connecting to a different input pin, but both input pins are 1s, so that means both N-type transistors are on, both are connecting, which means now we have a path to go from the output pin to the ground. So for the first time, the output pin is going to be a 0. All right. So that's the analysis process. Now, if you're thinking, but Tech, you're going way too fast, okay? Because I did go pretty fast. But the module actually talks about all of this. Okay, so if you go back to the module, it actually analyzes all 4 scenarios and even have pictures to show the connected transistors and the connected transistors and so on, and also one connecting, the other one is not connecting, one is connecting, the other one is not connecting. So basically everything that I just said, they're all in the module. You can read the module kind of slowly or carefully, just to make sure that you understand all the concepts. And the lecture is being recorded too, so that means you can, if you prefer a audio type of presentation, you can also watch the video again if you need to. All right, so now let's go back to Logisim, because what if Tech makes a mistake? Okay, that's one thing that you will probably learn really early on in this class is I make mistakes. Okay, so you probably want to double check things that I tell you. And in this case, it's easy because we can turn back on the simulation and we can now poke the pins. Now remember, if you want to change the state of the input pins, you cannot use the selection tool. You have to go to the poking tool to do that. So once you select the poking tool, you can go back to an input pin, and when you click on an input pin, it will toggle the state. If it was 1, it becomes a 0. If it was a 0, it becomes a 1. So you can see how if both input pins are 1s, the output would be a 0. If at least one is a 0, the output is a 1. If both are 0s, the output is a 1. And I think I cannot remember which one now. So, but you can see if at least one input is a 0, the output is a 1. Okay, so I think we understand the general idea of this circuit. But now the question is, what is it useful for? What is this? Right? That relates to the road taking activity. Okay, what was the word again that I used for road taking? NAND. Exactly, N-A-N-D. And there is no such word in the English dictionary, right? What? I mean, what is it? Well, the AND stands for negated. It is a negated AND thing. Okay. negated AND. What exactly is negated AND? So I'm going to use mousepad, which is basically my notepad, same thing. Okay, because this portion of the explanation is kind of more symbolic. Instead of having me handwriting stuff, I'm just going to type it. So when we say X NAND Y, it really is the same thing as exclamation point X ampersand ampersand Y. This portion here makes use of logical operators that you have already learned in CISP310. This part here is just using the newly discovered operator called NAND. So do we have any questions about this particular statement? X NAND Y is really just the same as the negation of X and Y. Any questions about this? All right. It's not OR, okay? It is a NAND. It is a negated AND. So let's check this out, okay? Let's check out the truth table. So we got X, we got Y, we got X. Well, we're gonna use the output over here, okay? So we already know that if at least one of X and Y is a 0, the output is going to be a 1. Okay. And the only time the output is a 0 is when both X and Y are 1s. Right? So this is what we have established by analyzing the circuit manually. So now what we want to do is to say, now for those, especially for those people who look at this and go like, but this looks like an OR. That looks like there's an OR somewhere in here. Okay, we'll take a look at what happens to X and Y first. Okay, so that's pretty easy. If you're using a simple conjunction, if at least one of the two things you are ANDing is a 0, the whole thing is going to be a 0, right? So that's going to be a 0. That's going to be a 0. That's going to be a 0. Oops. And that's going to be a 1 because this is the first time when both X and Y are 1s. So I'm fairly sure most of you can now see how I see it is just the negated of X and Y now. Right? So if you want another column for the negation of X and Y, then you have 1, 1, 1, and a 0 down here. This is the beauty of Boolean algebra. Okay, if you use a truth table and for every possible way to combine the inputs, you end up with the same value, then two things are the same. So this output is really the negated AND between X and Y, which is simplified as NAND. Let me take a look at the time. We got about 7 minutes left. Okay. So I'm pretty sure many of you are now asking, go like, so what? Okay, this is negated AND, okay, some kind of really obscure Boolean operator that we have never learned, never used, probably will never see again after this class. What is the big deal? Well, the big deal is everything that you know, everything that you use can be expressed as NAND. I'm pretty sure some of you are really questioning that. It's like, nah, that cannot be. We'll start with something simple, okay? We'll start with just the negation of X, okay? How do we express the negation of X using just NAND? This one is easy. Okay? Now, I would suggest as a ungraded assignment that you make a truth table for every single equality that I established here, okay? Because it is a good way to exercise what you have just learned. 2, you will start to appreciate why NAND as a very obscure little operator is actually quite useful. And 3, gives you something to do to kind of make sure that you're understanding the class material. So this one looks too easy. What about X and Y? What about just that? Okay, how do we use NAND to express X and Y? This one is going to look a little bit strange, okay, because it ends up as x NAND y NAND x NAND y. Because we exactly okay, so Foulin, Foulin just said the negation of x NAND y, but we know how to do negation already, so we just expand that negation to the expression NAND itself. Okay, all right. What about x or y? So what about x or y? So to explain x or y, we have to first understand De Morgan's law. Okay. De Morgan's law, which I'll explain, in a later module as well, basically says, okay, first of all, let me see if you guys are convinced about this. Does anyone want to challenge this? Double negation does absolutely nothing. Yeah, De Morgan's law, that is correct. That's the right spelling too. Okay, so if you look at this, okay, so first of all, we want to establish the equality that is in question over here. There's nothing to be afraid of. De Morgan's law is your friend, okay, because it allows you to do really cool stuff in Boolean algebra that no regular algebra can do. It's kind of cool. Okay, so if this is okay, then we're going to use De Morgan's law. So I'm going to specify on the side here what is De Morgan's law. De Morgan's law says if you have a negation of an AND, you can re-express it as the negation of the components of the AND connected by an OR. So it converts an AND into an OR by distributing the negation to the components. But it has a counterpart to this too. So if you have the negation of x or y, then you have the negation of the components again, but this time they are connected by a conjunction. That's De Morgan's law. And I'm pretty sure some of you are looking at this and go like, that is just weird, okay? If you're not convinced about De Morgan's law, use a truth table to convince yourself, okay? Use a truth table like this, okay? Except one column is going to be the value of this expression, and then the other column will be the value of this expression. If those two columns end up with exactly the same value for every single row of x and y, then the two expressions are equivalent, okay? And that's a very simple way to prove De Morgan's law. And once you have done that, I'm afraid that will also take the magic out of De Morgan's law, because it is no longer magical. It's like, oh, okay, it's just really mechanically they are the same. So don't be afraid of De Morgan's law. It is one of the most useful transformation in Boolean algebra. That's because the lab has not been released yet, which I will do shortly. But let's finish this discussion first, okay? The lab is going to be the lab, and I'll release the lab by 7 o'clock, okay? So now we can apply De Morgan's law to this component, because we need to somehow get an AND out of this whole thing, right? Because that's how we can reuse the first two rules that we have already discovered. So now by applying De Morgan's law, we end up with not x, not y, and those two are now connected by an AND. Oh, great! This is terrific, because we have a negation of an AND already. Alright, so now we have not x, NAND, not y. We still have the negation here, but we know how to deal with a single negation of something, because that is just the something and NAND itself. So now we end up with x NAND, x NAND, y NAND, y. So what is cool about this? Every operator that you have learned already in CISP360, they can all be expressed using a combination of a bunch of NAND gates, which also means the circuit that we are looking at here, this circuit can be used to create NAND gates, or excuse me, it can be used to create a NOT gate, an AND gate, and also a OR gate. All the favorite operators that you have used in CISP360, we can do all of those things by using various combinations of these 4 transistors in this configuration. That to me is really cool. Okay, even after teaching this class for more than 10 years, this is still kind of really cool to me. Sorry? Oh, I thought that was a question. All right, so moving on to the lab stuff. Okay, so I am going to release the lab right now so that you guys can see and participate. Okay, at first I thought that was a question for me, but turned out not to be. All right, so the lab that we are going to do, that you're going to do today, that I'll have to grade, is called Logisim Setup, and you can see it is not released yet. So I'm going to release it now. Okay, give me a second. All right, so the lab has an access key, so you're going to have to type in the password. So the password in this case is Logisim. I'll put it into the text channel too. So Logisim is the passcode, and I'm going to make it due at the end of the lab session tonight. So it's going to be June 7th, and it's going to be 8:20 p.m. Okay. So now you have close to 80 minutes, a little more than 80 minutes to do the lab. Yes. Yeah, so right after this, I'm going to turn off screen share and I will try to add you again. Yeah, if I still cannot add you tonight, it is not your fault. So I'm not gonna. I will give you some extra time to do it because there's no. I cannot. If I cannot add you, you cannot do the lab, right? So, yep, sure. And there are some additional questions. What do you need to install to do the lab? Just Java. It actually has the instructions to do it. You have to install Java. Just JRE is fine. The runtime environment of Java is going to be fine. I suspect your computer already has Java installed. You probably can test it. Yep. The access code is, I typed it at 6:51 p.m. That's why I typed it. Yep. No, that is not the one that we want to get, Eric. No. You have to download the specific one that is in the lab. The lab contains a link because I made changes to it. Well, for this lab, it probably doesn't matter that much, okay? But in future labs, you have to use the one that I have modified. Yeah, for the Yeah. It's only when you get to the part. Okay, it's not a part of the lab, but if you want to use the tester circuit to make sure that yours is running, that is when it won't work because the command line interface to specify an alternative library, as a component of the original Logisim, it in the documentation is there. It was never finished. So I finished that particular feature for the original author of the program. But it's okay, for this lab, it's okay to use that one too. Alrighty. So I am going to stick around to see if there are any additional questions. um Okay, so the question is, don't open it, download it, and then use the command line tool to open it. Don't double click it, just don't use the GUI. Okay, if you use the command line tool, it probably will let you do it. It's in the lab. Client, it is in the lab. The lab has a link to it. Alrighty, so I am done with the instructions. I'm just going to keep an eye on the text chat channel unless somebody has a question. It's Logisim. Okay, with two I's. There's an extra I between the S and the M. Alright, I'm gonna stop the screen share so I can do some stuff that I cannot screen share. So I'm gonna turn off screen share at this point, but I'm still on the computer, so if you type in the text channel, I can still answer those questions.